So we're covering transition metals, which is in the current edition of TRO, the 5th editions, chapters 25 and 26. And I've kind of merged these two together. I've had a certain way of teaching it for a number of years, and so it doesn't exactly follow either book. I have typed notes that you can refer to, which I follow a lot more closely than what you would get going through 25 and 26. So there's another interesting thing about the way I'm doing this lecture is I will be actually incorporating some older lecture materials in that I've recorded in the past that I think are suitable for reuse in this lecture. So transition metals, what are they, right? So most people think the D block elements represent what are called the transition elements, but in fact the D block includes zinc, cadmium, and mercury, which technically aren't transition metals. Transition metals are the elements with partially filled d orbitals. So the result is, these are kind of over here, these are anomalies. These are actually the transition metals. Now, they're labeled on this diagram 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the newer version, but I much prefer to call this 3B. This is 4B. This is 5B. And you can do Roman numerals, but I'll just try to stick with it like this. 5B, 6B, right? And you can see how that matches the headings. The only difficult part is starting with iron through nickel. These are all 8A, or 8B, sorry. So Roman numeral V, B. So they got that sort of designation of all being the same because they had very similar properties to each other, and it sort of never fell off. But it's useful to know because there are properties of those elements which are consistent with that small subgroup, including their sort of radii, magnetic properties, ability to alloy, things like that. So I kind of like that they're all grouped together for that. And then this would be 1B, and this is 2B, like that. So I prefer that. And in my diagrams, when I show you graphs, that's actually how I labeled the axes of the graphs, rather than saying the 3, 4, 5, 6, 7. I also, unlike what a lot of books will do, they'll call this the first period, the first row, second row, and third row of the transition elements. So if you hear row 1 or you see row 1 in a diagram, that's actually the fourth period. That's the first place the transition elements show up. So just in case there's diagrams you see online, you'll see a lot of times they're just called row 1, 2, and 3. I still like to refer to the actual periodic table period. These elements, which fit in here, lanthanum and actinium begin the lanthanide and actinide series are known as the inner transition elements. I normally like to begin this section by reviewing electron configurations and orbital diagrams. So we'll do that here because it's an important part of understanding the properties of transition elements. It has a lot to do with the number of unpaired electrons they have in their d orbitals, and that affects their ability to perform metallic bonding, which you probably learned about in Chem 1A a little bit. It affects their magnetic properties, their melting points, all kinds of things. And so I want to go over a little bit about electron configurations for that and orbital diagrams. So to start with, we're going to use typically something called core notation. So I'm going to start with an element. We'll start with carbon, and we'll do its electron configuration. So there's something called the Aufbau Principle, and I'm going to write it up above. We're going to reference it. And in the Aufbau Principle, it tells us the order electrons go into atoms. And it begins with the lowest energy orbital, and that's the one that's closest to the nucleus. So that's going to be 1s, and then 2s, and 2p, and 3s, and 3p, 5p, and then 4s, and then 3d. This is the beginning of the d orbitals and the transition elements. And then we'll have 4p and 5s, and then 4d, and then 5p, and then we're going to have 6s, and then 4f, 5d, and then 6p, and it repeats like that if you can see what the pattern is. I'll take you to the periodic table and show you that very briefly. So here's the periodic table I like to use from ptable.com. What we've been just doing is talking about the Aufbau Principle, and I'm going to show you now where it comes from the periodic table. This is the 1s, 1s orbital. You can put 2 electrons into it, so that represents hydrogen and helium, and this is the first period of the periodic table. And then we have the 2s, then the 2p, and then the 3s, and then the 3p. And if you remember, these are segregated into what are called blocks. So up to here, we have the s block. This is the p block on this side, okay, so going this way. And then in the middle, this is the d block, and this is the f block, like this. So the way you can generate the Aufbau principle is recognize that this is 1s, right, here. And then this is 2s, and this is 2p, and this is 3s, and this is 3p. Going back to our slide. Right, that's what I'm doing right here. 1s, 2s, 2p, 3s, 3p, 4s, and then 3d. So we're going to go 4s, and then this is 3d, and this is 4p, and the 4 comes from the period. And then you just have to remember that because of the way quantum mechanics worked out, the d orbitals spacings and energy spacings relative to the other orbitals are just a little bit below energy level, the 4s, or sorry, just a little bit above the 4s. The 4s is just a little bit below these guys, and so these fill first. Now, this is 5s, and this is 4d, and this is 5p, and then your 6s, and then we're down here. This is the f's, and those go down to 4. And so this is 4f, right? This is 5f down here, and then 6d, and then 5d, and then 6p. Again, keeping track of these are always n minus 1 if this is n, and these are always n minus 2. Okay, so that's how you can generate the Aufbau principle. Now, having said that, if you're going to do the electron configuration of something like carbon, it serves best to know what group it's in. So we're going to go over to carbon here, and we'll find carbon. Now, it's in group 4a, this is 14, just get rid of the 1 and think of it as 4a. So these guys all have 4 valence electrons. And then when you want to do the electron configuration, what you do is you can start with core notation and write the core for helium. So we're going to do like this, have 4 valence electrons. We're going to write the core for helium, and then what we're going to do is we're going to write 2s2, 2p2, like that. This total for the highest energy level make up the valence electrons, and so I have 4 there. Now let's do another one. We're going to do we'll do iron. We're hit our first transition element. That'll be down here. All right, and we'll look for iron, and we're going to figure out where it sits on the periodic table. It's in that first row of the d orbitals. It's the 1, 2, 3, 4, 5, 6th element from the left, right? So that means there's 6 d electrons. The core is argon. So I have 6 electrons here, and then I have 2 electrons here. So we're going to start with 4s, and then we're going to do the d's for iron. Okay, so we're like this. We're going to write core. Oh, I forgot to show the I don't know what that noise was. We're going to show the core for iron, that would be argon, right? So we're going to put argon in brackets. And then we're going to write 4s 3d. Now, since it's 3d6, that's how many we counted over, then the 4s must be full, so you can just put a 2 in there, remembering that s can have 2 electrons, p can have 6, d can have 10, and f can have 14. It's always, they go by numbers of integers, an integer number, like so 2, so this is 1 times 2, right? This is 3 times 2. This is 5 times 2. So this is 1, 3, 5, 7. This is 7 times 2. So it always goes by integer values. Now, having said that, we want to do the orbital diagrams. Let's go ahead and practice electron configurations. Go ahead and pause it, and then try to do the ones for chlorine and iron 3+. Okay, so here we have it. For chlorine, we'll go back to the periodic table. We notice it's here. Its core is neon. This is in energy level 3, so it's 3s2 and then 3p 1, 2, 3, 4, 5. Okay, so that's how I got that. Now for iron, all I have to do, iron 3+ ion, ferric ion, all I need to do is take 3 electrons off. Then the question comes, where do you take the 3 electrons from? And when you make cations in transition metals, you always remove the electrons from the highest principal quantum number, which is 4. So you take those first, and then you have to take 1 off. So I took those, and I have to take 1 off of there. So that's how I got this to be 0 and this to be 5. That gives me the 3 electrons I need to remove to make the +3 charge. So for all transition metals, you remove the s electrons first, and then you remove the d electrons. Okay, so what do orbital diagrams look like? So for orbital diagrams, we're really only interested in the highest energy level, the outermost shell that we're going to be dealing with. So that's going to be this part. Okay, so when we do orbital diagrams, you have to remember for orbitals, there's an s orbital, right? So like this, and then there's p orbitals that look like this. And you get you can put 2 electrons in each orbital. So when we're writing the orbital diagrams, remember you put 1 electron, and then you put another one, and then you go like this. You fill them. Okay, so a couple of rules called Hund's rule. We're going to go half. When you're filling orbitals, you put the electrons into degenerate orbitals. Separately before pairing. Okay, so Hund's rule says electrons in degenerate orbitals are placed separately before pairing with the spin parallel. And then I didn't put enough in there. I need to go to 5, so then the rest of them would go like that. But Hund's rule tells us how to fill the orbitals for elements who don't have completely filled subshells. Again, these are known as subshells. Anyways, what else is there about this? Another rule is Paulie exclusion principle. Now, you might have to go review why this is important, but in essence, Paulie exclusion principle limits us to 2 electrons per orbital. And basically, Paulie said you couldn't have N, L, M sub L, and M sub S be exactly the same for any two electrons in an orbital. And this, again, this is a review. I won't necessarily test you on these details, but basically that's what limits us to having two in each. If you want to, just very quickly, I can designate the values of N for this one. N is equal to 3. That's the 3 here. S, P, D, and F, right? Those are 0, 1, 2, and 3. So this is a p orbital, so that means L is equal to 2. And then M sub L has values from minus L to plus L. So for most purposes, this is minus 1, 0, and 1 for M sub L. So M sub L would be, for that one electron that I'm drawing the arrow to, that one is minus 1. And then the spin can be either plus a half or minus a half. So M sub S is equal to plus 1/2, like that. Okay? So the magnetic moment can only be either a value of plus a half or minus half. So that's what we have for that. Now for iron, this is really what we're interested in. This is the transition element. We're going to write down the orbital diagram. So we'll have something that looks like this. This is 4s and this is 3d. There are 5 d orbitals on any particular sublevel of d's, right? And then we can put 2 electrons in here. And then for the 6 electrons, Hund's rule makes us do this. And there are actually 4 unpaired electrons in iron. Okay. And then for iron 3+, what we would have is just this. Because I get rid of the 4s, and I'm left with 3d5. Okay. And it has 5 unpaired electrons. Okay, so that's kind of our review of electron configurations and core notation. Hopefully that'll help us make sense when I start talking about numbers of unpaired electrons and how it affects the properties. The next thing I want to do is go over effective nuclear charge, and I really should take you over to periodic table to do that. So that's what I'm going to do here. Actually, what I'm going to do, I just thought of this, I'll actually insert this as an image in this next slide so I can write on it and you can have it in your notes. Okay, so here's the periodic table. I went and stole it again. Effective nuclear charge is this. It's ZF is equal to Z, the nuclear charge, minus screening electrons. Now, it's pretty primitive the way we do it in the book. But the screening electrons are really what we'll just call the core. Whatever you're using for the noble gas core, we're going to treat that as screening electrons. So, for example, let's take sodium, right? Sodium is going to be equal to 11, that's its nuclear charge, minus the screening electrons are the noble gas core, it's the Ne, it's 10. So sodium has an effective nuclear charge of 1. Now, if you just sort of follow along with this, right, scandium, sulfur, sorry, scandium, I don't know where that came from, has 16 electrons, right? So sulfur has 16 electrons. Its core is still neon. So it has 6 as its effective nuclear charge. Now, what is the importance of effective nuclear charge, right? It's what attracts the electrons to the atom. So what happens as you go across the periodic table, there's a stronger attraction for the electrons to the nucleus of the atom because the electrons are all going in the same energy level, and as a result, right, they're all seeing the same nucleus minus the ones that are in the screening part of the nucleus, that is the core of the a screening part of the atom, the core of the atom. So, for example, if you think about, let's do pick something different. Let's do calcium. I don't want to do transition metal yet. Let's do calcium like this, right? Now, if you think about the nucleus of calcium, right? It has 20 protons and a bunch of neutrons, which we learned about in the last chapter. And then it has a whole bunch of electrons, right? It has 20 electrons. But the way those electrons are arranged is that energy level 3 gets closed off, in a sense, because energy level 3, like this, has actually 18 electrons in it. Now, period 4, quantum number 4, goes to the next higher energy level, and so those are the electrons that are further out. So this would represent energy level 4. And what happens is these inner electrons screen what the electrons on the outside see. Okay, so I have electrons over here that are trying to look into the nucleus. I put their eyeball on the other side, I guess. They're trying to look into the nucleus, but they can't see the nucleus because it's clouded over by 18 negative charges. So in practice, what we say is then its effective nuclear charge would be 20 minus the 18, which would give me 2. Okay. Now, when we're doing transition elements, right? All of these electrons are going into energy level 3. So they're seeing an increase in the effective nuclear charge the whole time, right here, in energy level 3, which is below energy level 4. So these energy level 4s don't really screen that effectively for these orbitals. It should also be said that the D orbitals don't do effective job screening the electrons on the outside, but that's just like a whole nother topic. But anyways, the idea is effective nuclear charge essentially increases from left to right on the periodic table. And that means atoms towards the right in the main group elements, so that's 1, 2, then 13 through 18, all get smaller, right, as you go from left to right on the periodic table. So this is going to affect the trends, right? So one of the trends that you learned in Chem 1A, this is smallest, right? And we also learned about ionization energy. Well, if you think about it, ionization energy is how hard it is to take an electron from the atom. So if an atom is smaller, it has more effective nuclear charge. That means going from left to right has more effective nuclear charge. That means the electrons will be harder to remove. So smallest radius is up here, but its largest ionization energy. Okay, so these are some of the trends that we'll be playing on, sort of reviewing some of the trends we'll be looking over in a little bit more detail for the transition elements. But again, this is somewhere where you might want to go back to your 1A notes and sort of review these trends. The other thing, which I alluded to, is as you go from bottom to top, they get smaller. And why does it get smaller from bottom to top? Well, you're at a lower energy level, and those are closest to the nucleus, right? The result is, though, that's why the ionization energy is highest, because these are closest to the nucleus, even though these all have the same effective nuclear charge. And you could think of it as, I have a small atom, and I want to pull an electron out to infinity with an effective nuclear charge of 1, let's say for hydrogen, right? Or I could take lithium, and I will pull it out to infinity. So this is Li, this is H. Right? Again, effective nuclear charge of 1, but look, it started up further away from the nucleus, so it's actually easier to remove because of that. Okay, so we're going to see a lot of these things play out when we talk about transition elements. Okay, so this is not Appendix 2 from your book. I stole this from a book years and years ago, and I like it. There's only one weird quirk in the way they list the ground state electron configurations, and that is they list it by energy levels rather than in the Aufbau Principle order. And in a lot of ways, energy levels make sense. They do core notation, so you don't have to look up all the inner electrons, because those are just all filled for example. If you really wanted to reconstruct, let's say, the electron configuration from nickel all the way from scratch, well, this is argon, right? So find argon and then put this, right? And then find neon, and then you would put that, and then find helium, and then you put that. And that would give you the complete electron configuration. You could just like backfill it by just following through the core notation. It makes the table a lot easier to look at. Now, people always tell me this. There's so many exceptions to the rules in electron configurations. I mean, why do we have to learn it, right? And my answer has always been, there really aren't any exceptions to any rules. We just don't know the rules yet. And so in these kinds of tables, there are a lot of areas where it looks like it's different from what we are taught, but that's just because you don't get taught everything at the very beginning. In fact, many of these were determined experimentally, and then later people have developed the explanations. So in a sense, they were exceptions, but again, they're not exceptions to a rule. We just don't know the rules. And for a lot of this is kind of understood now. But I want to look at a couple of them, and I put some red dots next to some important ones. You'll notice for chromium, for example, you would have expected 4s2 3d4, but instead it grabs the electron from the s orbital and shoves it into the d orbital. Okay, and then for copper, we see 3d10 4s1, and you'll see a bunch of those kinds of things that are down here. So let me explain to you like what we're looking at, okay? We're going to do it in terms of orbital diagrams. And I realize some of my dots and stars don't line up anymore. But chromium's electron configuration, you expect 4s2 3d4. And you can look at it in terms of our periodic table, which is here, right? 4s2 1 2 3 4 3d4. That's what we expect. What you actually get is 4s1 3d5. Now, it helps actually if you look at the orbital diagram, and you'll see what's happening. This is 4s, and then I have 3d like this, and I like to put a line here when I compress them, just so you can see this is 4s and this is 3d. You don't have to worry about where the margin is. And what I'm going to do is I'm going to put one electron here, and then I go 1 2 3 4 5. And it turns out there's something very powerful about the orbital symmetry of the d electrons when that subshell, the d subshell, is half filled. It's a conservation kind of thing. It's when you have a net magnetic moment of 0, and it stabilizes the atom. And anytime you can stabilize the atom, you make the electrons drop lower in energy. And in fact, we can see this. The atom is actually smaller than expected. It's not smaller than you observed, of course, but it's smaller than you expect it to be because of the electrons being stabilized by half filling that shell. Okay. Now, we see the same thing with copper. We would expect it to be 3d9 4s1, but in fact what it does is it takes the extra electron and pumps it up into this d orbital, in a sense promoting it, and when it does that, it stabilizes and then it drops in energy. So again, it's a little bit smaller than you expect it to be because it has an extra stabilization, which has to do with sort of this balancing of magnetic moments. You might think like, well, what does that actually mean? And my simplest explanation is you could carry a small bucket of water. Let's say it's like 4 or 5 pounds in your hands, right? And then you put one in each hand, and then you start spinning in a circle, okay? What's going to happen? Well, what's going to happen is, here's your stick figure U. Definitely not after Thanksgiving dinner because it's still skinny. But you're going to have a bucket in this hand. You'll have a bucket in this hand. That's your hand, by the way. I don't know how to draw hands. I can barely draw stickmen. And you have a pound of water in each, and now you spin, right? What's going to happen? Well, both your arms, if you spin fast enough, your arms will go out, but your body will stay centered, right? So that balancing of angular momentum stabilizes you. What happens if you let go of one of those buckets or you try to spin it without one of the buckets, right? Then you'll precess is what it's called. You'll wobble from side to side to side because your center of mass is not directly in the center of your body. And so what will happen is that creates instability. And so it turns out we see a lot of times, especially look at this series down in here where we're going to go to half filled, right here. These are half filled Ds, or completely filled Ds like these, right? Just like we see for copper and we see for chromium. And so we expect, because of its periodic properties, right, that a lot of the properties that we see in chromium will be exhibited in the elements that are in the same group. Okay, so for our purposes, chromium, molybdenum, tungsten, we expect to see the same kind of properties. Zinc, cadmium, mercury, I know they're not transition elements, I just told you that, but they will have similar properties, okay? Oh, wrong way. Other thing I wanted to note, I highlighted some of the highest melting point locations of the highest melting points. But rather than look at it like this, I kind of remade a whole bunch of slides, and now we're going to be looking at the properties as we graph. We're going to graph particular properties and try to understand how that, why they are the way they are, based on relationship to effective nuclear charge and other sort of electron interaction things.